My talk today is fatigue crack detection for CFRP Composite pressure vessel using Mechanoluminescent sensor. First of all, I'd like to introduce a background and the goal of this study. This figure shows a sample of fuel cell vehicle with a hydrogen tank. For decreasing the weight of the tank, the novel composite vessel has been utilized for the vehicle. It is composed of inner aluminum liner and outer carbon fiber reinforced plastic layer. For driving the vehicle, this pressure vessel is repeatedly filled and released by high-pressure hydrogen. Such processes induce fatigue cracks in the aluminum liner, and finally, progress cracks leaks the aluminum liner and hydrogen gas leaks through the cracks. The goal of our study is to detect such fatigue cracks of composite vessel before pressurization. To achieve our goal, we utilize a mechanoluminescent sensor. The mechanoluminescent sensor, called sensor for short, is produced with fine powder of European doped strontium aluminum oxide. The powder mixed with a binder can be painted on the surface of various structures. And this movie shows some demonstrations of ML sensor. The sensor was painted in the car, and you can see visible light emission is observed at the scratch point and the front part. And this is a ball with partially painted sensor, and the light emission pattern can be observed. These light emissions are induced by mechanical deformation. This means that stress distribution on a structure surface can be visualized directly. If there were some defect in the structure, the ML sensor might show specific pattern. So we are applying this ML sensor to structure monitoring. At first, we examined ML pattern by composite test piece. The test piece is composed of CFRP layer and aluminum plate with 3 notches. The ML sensor was painted on the surface of CFRP layer. The depths of the notches are 0.64 and 0.37 and 0.28 millimeter respectively. When the test piece is stretched, light emission pattern is observed as shown in this movie. At the position of the 3 notches, light emission linear intensities decreases according to the depth of the notch. In case of composite vessel with fatigue crack, similar ML pattern would be expected to be observed according to the progress of the cracks. Let me explain our experimental setup. This figure shows an examined CFRP composite vessel. MLPET sensor was coated on the whole surface of the vessel. The vessel was periodically pressurized by this high-pressure water pump. Light emission images from ML sensor were observed by 4 CCD cameras for side view and 2 CCD cameras for top view. The experiment was carried out repeatedly on set of 2 experimental modes. One is continuous mode with 200 pressurization cycle, and another is high sensitivity mode with 5 cycles. In the later mode, ML images with high signal noise ratio are obtained. And this movie shows an example of ML images observed in high sensitive mode. After 43 pressurization cycles, a fatigue crack breaks the non-liner. However, at a glance, we cannot identify the ML pattern produced by the fatigue crack. An important property of such pattern is to vary according to progress of fatigue cracks. Therefore, we should observe fluctuation of ML pattern. To avoid influences of various noise, precise differential images are required. In this study, for this requirement, we applied principal component analysis to time series of ML images. Based on the statistical property of dataset, compact and efficient projection can be obtained by PCA. For example, a dataset expressed by 2 parameters, x1 and x2, distributes as shown in this figure. We obtain new parameters z1 and z2 by applying PCA. Important thing is that this z1 shows a direction of maximum variance of dataset. Then ML image in pressurization cycle is assumed as a point in a superspace of each element. Such point distributes in the superspace according to the pressure value. As a result of PCA, it is expected that the first base provides a normalized ML pattern because variance due to the pressure is larger than that of noise. We examined our idea with experimental data set. This figure shows reconstruction of ML images by using PCA results. Time series of ML images are expressed by this orthogonal expansion equation. As you can see, the first base images, the first base image has maximum component value. It means that we can consider the first base image as a pure ML pattern. Okay. These movies show the first base images of every high-sensitive mode of 4 side view cameras. You can find patterns of carbon fibers in these images. In the movies of number 1 camera, a slight indication pattern of fatigue crack appeared at last image. By simple subtraction among past base images, fluctuation of ML pattern is extracted. Above image is the first base image of number 1 camera at 4400 cycles. After 43 cycles, a fatigue crack penetrated the vessel. Below image shows the first base image at 4200 cycles. Subtraction of above image minus below image shows the right one. As you can see, there is characteristic pattern at this location. This pattern means that the ML intensity decreases as same as the case of previous composite test piece. Just below the photograph shows identified location of the penetrate crack. The location of the pattern is coincided with that of the crack. After experiment, the aluminum liner and CFRP layer of the examined composite vessel is separated. Above photograph shows outer side view of the aluminum liner. As a result of inspection on penetrations, the fatigue crack was found at this location. Below photograph shows microscope view of identified fatigue crack. These photographs shows inner side view of the found fatigue crack. Excluding this crack, no fatigue cracks can be found, as well as no characteristic patterns are found in the base images of other cameras. These are conclusions of my talk. That's all. Thank you for your attention.